slides.
Okay, super. So Gary Holmgren will be speaking to us about his experiences at Kennedy.
All right. Just gonna get the sharing code ready.
Everything okay there, Gary?
Yeah, I'm just trying to get the meeting ID so I can share it. I'm on Google Slides. One moment. Maybe I could just share my screen then.
Yes, you should be able to share your screen.
Oh yeah, I think I'll just do that. All right. Can you see the presentation? All right, it should be loading. All right. Sorry for that. All right. Are you able to see it?
Yes, go ahead.
Oh, very good. Thanks for bearing with me there. All right. So hello, everyone. Thanks for being here. My name is Gary Holmgren, and I will be presenting my internship experience over the last spring and summer at NASA's Kennedy Space Center. I went to college at Century College in Minnesota, working towards my bachelor's in aerospace engineering, and I plan to transfer to the University of Minnesota this fall, hopefully full-time, to finish my degree. So let's see if this loads. Okay. I'm not sure why the next slide isn't loading. There we go. Well, very weird. Does it just show a loading screen for you?
Yeah. Yes, that's what we see is black screen that says loading.
Okay.
There it is.
I'm just gonna do it like this instead of the present. Well,
That's great.
there's some videos in there, so I think it might be slowing it down. I was hoping to play those videos for you guys. Let me just try presenting it to the meeting. See if it works that way. Okay, guess not. All right, well, there it showed up. Sorry. The Advanced Image and Analysis Laboratory is where my internship position took place at Kennedy Space Center. And this lab is located primarily in the Vehicle Assembly Building, or VAB, shown on the left. And this is the home of all specialty imaging needs and analysis needs within NASA's Kennedy Space Center. Image analysis with photogrammetry is the primary function of the lab, and that is where the lab team members work with other engineering teams to get high quality imagery of subsystems being tested. A lot of the time, video is captured using high-speed cameras as the subsystems and mechanical assemblies are being tested. They are moving fairly rapidly, and they're using this high-speed footage to and use analysis in software like the interface shown on the right to determine the speed, the acceleration the components are traveling at, the distances they're traveling, and other aspects of how they might affect other parts in the assembly. Play a video. So in the video shown is the umbilicals that connect the mobile launcher to the SLS rocket. And that's a good example of what the image analysis lab uses or performs. 1 second. Sorry, all right. So that's a great example of how the image analysis lab tracked the umbilical systems that attach to the SLS rocket, and they provide that data to engineering teams to ensure that those umbilicals are within operational spec so they work properly on launch day. They track components on the umbilicals like that in 3 dimensions using what's called photogrammetry. And that process involves taking images from multiple angles and stitching them together with interpolation. To do 3D tracking of components requires more than one camera view, and specific measurements between the cameras must be known to create an accurate 3D model of the traced component. So the current camera capabilities at KSC are these 3 shown here, the first being operational television or OTV. These systems typically contain high resolution cameras with zoom capability to give engineering teams and the general public good views of the rocket and subsystems during launch operations. And the next being high speed, used for engineering analysis mostly. And lastly, tracking cameras. These are used for long range viewing after the rocket has launched and becomes out of view for traditional cameras, which happens very, very shortly after launch due to the nature of the rocket's speed. More about the OTV system or operational television. The pan and tilt mechanism for the OTV camera ranges from around $10,000 to $30,000 each, as they are very robust and capable of handling blast loads from a launch. A wide variety of cameras can be placed inside the protective housing shown. Infrared cameras are also used in these to provide views of hydrogen lines and systems, since hydrogen burns only show up in the infrared spectrum. This housing is also usually filled with a nitrogen purge during launch to create a higher pressure environment inside as opposed to the pressure outside from the rocket exhaust. You definitely don't want that stuff getting into the electronics, and you'll find that almost every system on the mobile launcher has a positive pressure nitrogen purge on it due to this. In the lower right clip shows the vibration test laboratory at Kennedy Space Center, and it shows how well the isolators can dampen the loads going into the camera inside. The loads generated by this test are similar to what they expected to see on launch day. The camera was mounted on the mobile launcher platform, so the resulting video still shakes extremely violently and is up to the image analysis laboratory to stabilize the video in post-processing. I think it was around 23 G's of force going into that test. High-speed imagery. As discussed earlier, these cameras are used primarily when analysis is needed on subsystems that move fairly quickly. On the left is a high-speed digital camera, which costs just over $120,000. but it can film 4K at 1,000 frames per second for about 15 minutes before it runs out of storage. On the right-hand side is the high-speed film camera, and you may ask why they are still using film. And that's due to the sheer cost of replacing these cameras and housings already built and welded to the platform of the mobile launcher, which was actually recycled from the space shuttle program that also used film since high-speed digital wasn't feasible at that time. High-speed film cameras do have better sensitivity or a higher dynamic range for bright scenes, so it does better at capturing still imagery despite the boosters being as bright as the sun. This is really the main advantage. And other than, other than that, digital is better than in almost every other way from a cost and functionality perspective. After the launch, the film is shipped to Atlanta or New York and processed by Kodak, which isn't the quickest turnaround, but high speed can be processed almost instantly. So the working environment that these cameras are placed in is very close to the rocket engines, as you can see in the right-hand photo. In the video on the left, you'll notice a shockwave from the solid rocket motors igniting, which destroyed a lot of components on the mobile launcher actually during the last most recent SLS launch that took place. And it's pretty impressive how these camera housings are built to withstand these environments. And lastly, we have the tracker cameras, which are human operated, and they run upwards of a couple $100,000 or more each. And these are outside the blast radius of about 3 miles from the launch pad. And since people aren't allowed within that, these have to be placed at those locations since they're manually operated. These views provided with the trackers are necessary if the rocket needs to be viewed from with usable definition during the later stages of its launch, since it's so far away. But the quality of the imagery is highly weather dependent on the cloud cover and lighting. And the right side is a older clip of a shuttle launch on a clear day, and you can get some nice views from these as they have fairly large focal lengths. Right, now that we have an overview of the image lab and its operations, I will discuss my project there. Originally called the Autonomous Camera Tracking Platform, this was my mentor's idea after working in the lab and seeing a need for an advanced new imaging system. The system needed to be autonomous to eliminate the need for manual tracking of launches, which is currently how all cameras are operated at KSC. The autonomous function, combined with the ability to generate point cloud models of having multiple cameras placed around the launch vehicle, can provide a significant advantage over manually operated fixed cameras, which sometimes can't provide all the necessary views needed during launch operations. When you have 2 or more cameras and you know the distance between them, you can create the 3D model, which is the basis of the future of this project of having a scalable system. So this was a fairly new project, and as I was the sole intern working on it during the time, there hadn't been a design established yet. So my mentor left it up to me to have creative control over the mechanical design. I started brainstorming some concepts and looking at existing systems. And when I got a good idea of the operational principles of a pan and tilt system, I started modeling one in CAD with Creo Parametric. The image shown here is my resulting design, and it features a belt drive that allows for independent panning and tilting, a protective housing for the stepper motors, controllers, and microcontroller, and also a switchable camera mount that allows for various cameras to be attached. In the future, this system will use both DSLR and high-speed cameras. When the design was done, I had to give it a name, so I came up with a good old NASA acronym and eventually chose SPIDER, which stands for System for Photogrammetric Imaging Detection and Ranging. It's a lot to say. And the idea encompasses many of the abilities of separate camera systems into one. And this was really a selling point on a proposal my mentor and I worked on when we submitted to NASA for project funding, which was most recently approved as of a couple of months ago. And this is the final prototype. During the summer, I was able to 3D print some main parts of the structure of the design and began to assemble it. I used Formlabs to print the housing from rigid resin for a smooth and durable finish. After assembling everything I had time to manufacture, the project was starting to take shape. And the next steps of the project really is to utilize the funding for manufacturing the rest of the components of the final assembly. At that point, the computer vision baseline code can be integrated with the camera system, and the software is currently being worked on by another intern, and I plan to continue working on it this summer as they have asked if I'm still available, and of course I would love to get it up and running. After it's functioning at a basic level, the system should be able to demonstrate reliable tracking of objects before converting the design into a field-ready version that can go through the various stages of approval for hardware at NASA, which can be pretty rigorous, as you've seen in the vibration testing video. I wanted to give a special thanks to my mentor, the Minnesota Space Grant, and all the amazing folks at Kennedy Space Center for providing an invaluable internship experience. Each internship I've done has been incredibly memorable, and I've met a lot of wonderful friends along the way as well. So I do have some advice for those who want to get involved at NASA that have not yet. And those are to make sure to check out the space programs if you haven't already, as they really open the door for me to get involved in projects and research with NASA. It also builds great experience, and you'll develop useful skills throughout that academy. They have two academies. One is the Proposal Writing Academy, where you learn to write and review a proposal in the NASA manner, and the Mission Concept Academy, which is where you work with a team of students to design a conceptual mission and write a preliminary design review on that. Second is to show that you're passionate about your work and determined to excel in your field. Mentors will definitely take notice when reading your resume or interviewing you for positions when they see this determination. It may sound simple, but apply for everything you can as long as you're qualified. NASA has many internships open each semester, and although not every one of them sounds extremely exciting, you would be surprised that almost all of them will exceed your expectations. I personally never thought I would have wanted to work on cameras or imagery before, but now reflecting back, I couldn't have asked for a better opportunity. And lastly, make sure to reach out to mentors and NASA personnel with project interests and application questions. Do some research, find out who the point of contact is for some of the projects you're interested in, and reach out, because mentors love seeing people taking that initiative. Most applicants won't actually reach out, so this would instantly give you an advantage over the other applicant pool. And thank you. That concludes my presentation. I appreciate everyone for watching. Sorry for the technical issues. Thank you for bearing with me. So does anyone have any questions?
Thanks, Gary. Questions? Ben?
You mentioned that they were still using film cameras and looking into the benefits, disadvantages of film cameras cost. Where do they get the film? Right, I mean, like that, are they like contracting with Kodak?
Sorry.
Right, because I can't imagine that film is just like something that everybody uses, right?
So you're asking where they got the film, and if they have a contract with a company like Kodak?
He thinks that you can't buy film anymore.
But I think you can buy film, but you know, I mean, there
Oh.
can't be that many people doing high-speed camera work
Correct.
using film.
Yeah, I believe from what I remembered hearing the lab technicians talking about is they do specifically make some film just for the purpose of NASA to use it, since they're likely one of the only customers they have. And they do have a contract with Kodak, yes.
I have a budgetary question. We supported you last summer, but you actually started working at NASA before last summer. Do you know who supported you before we did?
So in the spring of 2022, that was funded by the, I think it was MIREP Foundation, or it was the National Space Grant.
Okay, so it turns out that NASA reaches out to us if they can't find other funding, but in this particular case, they did find other funding, and then they wanted to keep you on, and then they came to us, and this is all well and good, but you should apply, just like you said, apply.
Yeah, there's many positions open. I mean, there's, several hundred or more each semester. So I would just apply to as many as you can. And there's, as long as you're qualified, of course, and reach out, find who the mentors are. You could probably do some searching on LinkedIn. That's usually what I would do.
Yeah, I think in nasa.intern.gov, something like that. A couple months ago, I looked and there were like 500 separate descriptions of intern. And somebody was at a conference recently, somebody was complaining to me about how many of them don't get filled at all because nobody applies to them. They actually don't fill them all because some of them have 0 applicants, literally.
Yeah, because people, don't think that they might be not exciting or who knows, but a lot of the times, a lot of those internships are really exciting and they'll definitely exceed your expectations. So you have pretty good chances if you apply to all of those.
Okay, Gary, thanks so much. We'll go on to our last speaker, but thank you again.
Yeah, thanks everyone.